All right, students, I wanted to do a video about exponential derivatives from first principles and then also connect to why a certain special exponential is invariant under differentiation. So let's just look at a general exponential equation, y equals a raised to the x. So then if we look at our derivative, limit as h approaches 0, of a to the x plus h minus a to the x over h. We can use our property of exponents to write that as a to the x times a to the h minus a to the x over h. You can factor out the common a to the x, and you can even pull it in front of the limit because a and x don't involve the letter h. And so if you factor out a to the x, you have a to the h minus 1 over h. And so what we know now is that your derivative is equal to a to the x multiplied by something. And this right here, this something right here, we can just call the letter k right there. We'll deal with that in a little bit later here. But basically what I'm showing you so far is just that the derivative of an exponential function is itself times a certain constant. And so then a sort of natural question comes up, which is, when is that constant equal to 1? So let's consider that situation. Let's say k is equal to 1. When does this happen? Well, this happens if a to the h minus 1 over h is approximately equal to 1. Because remember, that's what a limit means. A limit means that eventually, as h approaches 0, it will be approximately equal to 1. So we can multiply by h and get a to the h minus 1 is equal to h, or a to the h is equal to h plus 1. Really, I should still be saying approximately equal to. Now, this doesn't seem very exciting yet, but I can raise both sides to the 1 over h power, and I get h plus 1 to the 1 over h. I'm going to make a weird little substitution here that makes a nice connection. I'm going to say the letter n, which I haven't used yet, is equal to 1 over h. And that's okay as long as h is not exactly equal to 0. So then if I rewrite what the letter a is equal to, then we have 1 over n, because if n is equal to 1 over h, that implies that h is also equal to 1 over n. Then I have 1 over n plus 1 raised to the n. And the other piece about it is the original k value was looking at the limit as h approaches 0. So this is a little bit of an interesting idea, that if you have the limit as h approaches 0, that turns into the limit as n approaches infinity, because we defined n to be 1 over h. So we can switch back from talking about things being approximate, so I should still have my approximations here, to being exact, that a is exactly equal to the limit as n approaches infinity of 1 over n plus 1 raised to the n. And you may not recognize this, but historically, the number e came out of this question right here, which is looking at an investment at 100% interest compounded infinitely many times. I believe it was Bernoulli who was studying it at the time. One of the Bernoullis, there were several, was studying it at the time, was looking at like, well, if you do 100% interest compounded once, you end up with $2. If you have 100% interest compounded twice, then you actually end up with more than $2. You end up with a 50% interest for the first one, and then 75 cents for the second one, because you're compounding the first 50 cents. So you end up with 225. And as you increase the number of compounds, the total amount of the investment increases, but it doesn't go up forever. It reaches a certain limit. And so the limit that it reaches at an infinite number of compounds turns out to be the number E, Euler's number. So this whole diversion over here was just to show you the special case that if your A value is equal to E, then your derivative is equal to E itself, E to the x itself. Now, what ends up happening in general is that the K value is related to the E, that the K value in general turns out to be the natural log of A. And that just comes from the same idea. It's a little bit beyond the scope of what I wanted to show you here, but it comes from the same idea that you are multiplying by a constant and that the number E is involved in determining how big that constant is. So in general, the derivative of an exponential function is itself times a constant. That constant is equal to 1 when we're looking at the number E, and that constant is just equal to the natural log of the base in general. So please comment or ask a question if there's anything that I can do to help. Thanks.